who are involved. So my first question would be, who has worked with JAX before? Just to have some idea of like people are familiar with JAX in general. Yeah, so minority. Okay, I'll try to make this a little bit of a sales pitch in that case, to try to convince you why in some cases you might want to work with JAX. And I'll start with a bit of a motivational long-term vision of our project. I'll introduce one of the papers, which is JAX-LOB, which is a simulated limit order book environment purely written in JAX. I'll go a bit into the background of sort of why that is maybe useful and some of the information, what the problems are if you want to do something like that in JAX and the benefits, and then how you could use this for reinforcement learning. So this is ultimately where we want to go with our research. So to have a very fast simulation that you can run reinforcement learning efficiently. And then I'll go a bit into to give you an overview of a generative model that we've built for limit order book data. Okay, let's get started. So just as a sort of, yeah.
Can minimize the.
Oh yeah, sorry.
Yeah. Yes. Yeah.
Okay.
Brilliant. Yeah. Thank you.
Okay. So ultimately, where we want to go with this is to have a multi-agent simulation. So I'm probably preaching to the choir why that might be useful, with individually rational agents that produce aggregate data that is actually representative of the real data you see. So you have low cross entropy. And the start of this we thought might be interesting is just start with a single agent reinforcement learning, sort of build this up from the ground. Then the problem is if you have a single agent and you're training on historical data, the historical data is fixed. It doesn't actually change depending on what actions you take in this environment. So you need some dynamics in the background, where we thought the first step you could try is just have a generative model. So conditional on the actions an agent takes in this environment, you can have a generator that plays the environment and reacts dynamically to what the agent is doing. Ultimately, we want to take this into the multi-agent direction. So instead of one RL agent, you do multi-agent reinforcement learning training with the background either being static data or generative model. And ultimately, you hopefully can do away with the generative model and just have a full simulation of individually rational agents. So that's sort of the roadmap we envision for our limit order book simulation. So what are the benefits? Why do we want to do this? So one thing is market impact. Everyone who's at least a practitioner who's caring actually about the implementation of strategies or people doing something in limit order book environments is you want to accurately have an impact of your orders. You want to see that if you reveal what you're doing, people are reacting to it, you're pushing the price against you, and everything becomes way more complicated. And these indirect effects are often omitted in research just because they're really, really hard to model. But that's not all. Like ultimately, we want to have a realistic agent-based simulator that doesn't rely on any rule-based, either square root law, market sort of price impact rules, or that doesn't have any hard-coded heuristics, but that is learned ideally with individually rational reward functions, for instance. Okay, so this is. Maybe you're aware of this research direction of Applied that people at JP Morgan originally developed, which is like a multi-agent simulator with like an event-based queue that you just purely implemented in Python, and it's super generic, and you can do a lot of different things with this. But there are some problems with it, which is why we developed our own simulator specifically for limit order books in JAX. What's the benefit? So first of all, it's hardware accelerated. So you can run your entire simulation on the GPU directly. That's nice because if you want to do machine learning as well, that's running on your GPU already, and you don't need to move things between memory. So it's way faster. Our simulation is specialized for limit order books. So the code is made for limit order books, not for generic discrete event simulation. With JAX, you can JIT compile your code. So if you give sort of the dimensions of your data types, first time you run the Python function, everything is compiled onto the GPU, and you don't run into the problem of slow Python code that's runtime interpreted. Our simulator is purely functional, which is sort of dictated by JAX, so it's relatively easy to extend and just, for your own use cases, write extra functions that build on top. And this is built with parallelization and reinforcement learning in mind. Okay, then I already mentioned part of this step is a generative model, because we want to have realistic impact, so that agents sort of react, or you model what the market as a whole would do if you take action A or take action B. This is sort of our black box solution concept to get something like an adaptive order flow. But also we want to have a really granular model. Most generative models so far model return series or mid-price series, so relatively low-dimensional data. And what we wanted to do is actually model the message by order data, so all the messages you see in the limit order book with a generative model. So you can think of this similarly to maybe a language model, where you autoregressively generate tokens that sort of over the course of the generation make up messages, and these messages are then submitted to the simulator, and so you can sort of simulate generatively what would happen in the market. Okay, I'll go into detail about this later on, but I'll just want to give you a bit of background on the JAX-LOB. So I already said the benefits are it runs natively on GPU. We're doing the RL training already on GPU, so that's a double benefit. You can JIT compile it with an XLA compiler, so this is blazingly fast, and you can get like orders of magnitude speed up compared to pure Python implementations. And there's a seamless integration with now a relatively big JAX framework. So for instance, GymNax, which is the gym equivalent that you might know from reinforcement learning in JAX, pure JAX-RL, which implements common RL algorithms in JAX. There's JAX-MAL for multi-agent reinforcement learning. Some of these have been developed in Jakob Foerster's group at Oxford. And NumPyro if you want to do probabilistic programming. All of these things are sort of natively built into the JAX framework. And this is probably like one of the key figures from the JAX-LOB paper. Compared to like a NumPy implementation of a limit order book, you get a 75% speed up if you run this on GPU and you parallelize sufficiently. So if you think of RL training, which might take like a few hours to train relatively simple problems, this speed up is really a big push in the right direction if you want to bring this to a bigger scale. We're focusing on RL, but in principle, you could use this for other things like Monte Carlo simulation or any sort of distributional rollouts that you can do in parallel. So I'd be interested if anyone working with LOBs would want to sort of build on top of this. This is, I think, a nice platform at this stage. Okay, I think I'll go briefly only over the background. We're using data from the Lobster data set. People might be familiar with that, I'm not quite sure. But essentially you get data from NestStack limit order books, where you have limit order book states, and you have messages that correspond to changes in the order book. There's some limitation of the data, but I think that's not that relevant now. Okay, so this is sort of what the limit order book representation looks like. I think everyone working with this kind of data would be familiar with this. So this is an example of like what a cancel order might do and what changes if you submit these orders. I'll skip over this. Okay, so why hasn't someone else done this before if JAX is so great? Well, there are some limitations if you want to do this. So one thing is your arrays have static shapes. So the first time you call a function for this to be JIT compiled, you need to already know how big your maximum sort of number of orders are. You can't use data types like queues or red-black trees that you would use if you wanted like an efficient implementation in C++. And you have somewhat restricted control flow in Python, so you can't just write your regular for loops and your while loops, but you actually need to use JAX-specific control flow primitives to make this work and make it fast. One problem, especially with the data types, so that you don't have queues or linked lists and you only have arrays, is how do you deal with the sorting? I mean, it's very important in limit order books. It's usually a queue. You need to execute against the person who has the best price, usually price time priority. The way we handle this is we usually don't keep the orders ordered at all times, and we just get sort of the best order at the time when we actually need it. So if you're executing something, if you're just submitting new orders, these can, in principle, just go somewhere in these arrays and just wait there until they're needed. So that's sort of part of the choice we made in the implementation. I already said, essentially, we are just keeping two big arrays of bit side and ask side, and these things are not ordered all the time, and all the empty entries are just filled with -1. So all these are just integer arrays, really fast, low-level implementations. Okay, another problem. We want to make this fast to parallelize. If you do reinforcement learning training, you want to run multiple environments of your order book in parallel. And for that to work well on GPUs, if you have some branching, so like a if statement as a simplest case or sort of a switch statement, the slowest one would usually hold up all the other elements of your branch. That's just part of like how GPU architecture works. So you can see here, for instance, a crossing limit order that might eat through the book might take longer than just a limit or a cancel order. So this is sort of your this is what gives you the time you actually want to optimize. Okay, we've, I think, made some good choices to make this faster. As I said, 75 times faster. So I'm going to show you a brief example of how you could use this for reinforcement learning. So this is still ongoing work. We haven't published on this yet, but we're trying to do reinforcement learning for optimal trade execution, where the task can be easily described as you want to sell a number of shares over a fixed time period. So it can be 30 minutes or 10 minutes or 1 minute, whatever you want. And you want to optimize slippage, or also called implementation shortfall, which is essentially your revenue you get from selling relative to how much revenue you would have gotten if you could sell everything immediately at the beginning of your training episode. And so far, this training curve is just sort of in-sample data, so this doesn't really show you how well this would perform on unseen data yet. But there was just a proof of concept. You can parallelize the training over 1,000 environments, which really wouldn't be possible if you use any other paradigm that isn't hardware accelerated on GPUs. Okay, then I'll switch gears a little bit and get into this generative model a bit more, which is also one of the applications of the JAX-LOB. So this also uses our simulator. So one thing, generally, if you want to use deep learning for limit order book data, is that you have a highly non-stationary representation of the data, right? Your prices between stocks might be highly different. The prices of the stock between different days are completely different. So we wanted to first find the data representation that actually works better for these deep learning models. So we try to make it more stationary, for instance, by encoding prices as tick deviations from the mid price at each point in the book. And then you just have an extra time series that gives you price jumps of the mid price. So really more stationary. Next thing is, we thought, why can't we do the same thing people do with language models? Why can't we autoregressively model this data similar to text? Okay, if we want to model messages as text, we need a tokenizer. Because we came up with one tokenization scheme, where on the top here you see one message. In this case, this is a deletion of a limit order, where you have fields like the type of a message, delete, so direction if it's a buy order. You have a price, you have a size, then you have the inter-arrival time when this order came relative to the previous order. You have the time of day, and then we're encoding which message is this about, which one do you want to cancel. And that's the one that was submitted at price, mid price -8, with this size and this time stamp and so on. So you have sort of the new message, and you have a reference part. And what we're doing now is we're just using a numeric tokenizer that splits up this message into either individual numbers or individual groups of numbers, and those are then essentially one hot encoded, similar to a language tokenizer. So you can see this example. The price here from -9 gets converted into 2 tokens. One token gives you the minus, so the side of the book, and the other one gives you the price level. And for some fields, we share vocabulary. So the time fields, for instance, they're using the same individual tokens, but the prices and the sizes have a different share of the vocabulary. Please also stop me at any point or ask questions if something's unclear. Another problem is the timestamp, for instance, because times are, usually to nanosecond precision. So you have lots of individual digits that you need to tokenize. And we already know from large language models that they're not particularly good with precise computations of these numbers. But we tried anyways, of basically splitting up these timestamps into sequences of 3 digits that each get converted into a single token. Okay, what sort of deep learning architecture are we using to make this work? There's an interesting paper called basically that introduces this S5 layer architecture, which stands for simplified structured state space layers for sequence modeling, which is, I think, essentially a fancy recurrent neural network layer that works really, really well for long sequences of multiple hundred or thousands observations. And the way this works, it's a discretization of a linear state space model. So in the top right, you can see a simple state space model with an input process U and a hidden state X. And then you have a linear relationship to this where it describes the state change of the hidden state. And then you have an output projection Y, which takes this hidden state, and also, if you want, you can bypass in the input for the output as well. And this is sort of the, I don't know if I have a point here, but this is how this looks in the architecture space. You just take in one input sequence, you get this to the hidden state, and at the end, you have a nonlinearity added. So you can stack these similar to recurrent layers in a deep neural network. Okay, and we're then combining multiple of these S5 layers into 3 different modules, where sort of the top left module takes the message data that we have from Lobster, which we've tokenized. The bottom left would be an encoder for the book module, which takes your volume series of, okay, so this might be a bit unfamiliar, but essentially we are re-encoding limit order book state. Instead of having prices and volumes, we are just having volumes around the mid price. So for mid price plus 1 tick, you have 1 series. For mid price plus 2 ticks, you have 1 series, which gives you sort of this image snapshot representation of what the book looks like over time. So these individual modules are then just concatenated and put into further processing with, I think in our case, 6 of these S5 layers. And ultimately, what you want to do is you want to have a distribution over the next token in the sequence, exactly like a language model. So you're predicting a distribution over the vocabulary, and then you can either do argmax sampling, or you just sample proportionately to the distribution that your model is predicting. Okay, so once you've trained this, you can then do the generative part. So this works in 2 steps. So that the inner process, the token generation loop in white, which takes in your masked message sequence, sorry. Masked, I mean, you just mask the next token in the sequence you want to predict. And you take in the order book sequence, and you sample a token from the distribution, and then you append this to the message you want to predict. If it's done, if you've generated an entire message, you move on. If it's not done, you go back feeding into the generated token, so you can condition on your generation and sort of continue in this process. Okay, let's say that the message at t+1 is then complete, so you go outside of the white box, and then the question is, are there some semantic problems with the message that you can check? So for instance, is it generating a delete message that doesn't actually exist in the book at the moment? If this happens, sometimes you just discard the message and you start over again. And if not, if everything's fine, this message goes to our LOB simulator that updates our LOB state and inputs the new state in the generated message into the book. So sort of it's an autoregressive process for generating new data. Does that make sense? Awesome. So hopefully with scale is what we're thinking. If we just scale up this model, this error correction process might not be necessary anymore. Currently, it's a relatively small model with, I think, something like 6 million parameters. So similar to language models, GPT-2 also made very incoherent sentences sometimes. It doesn't always work, but we've seen that scale actually, both in like model size and data, changes these things quite dramatically. And this is some fun follow-up work we're currently doing. Okay, let's look at the empirical performance of this generative model. So we look at two different stocks here, Google and Intel. So the first one is the mid-return distribution up to 100 messages into the future, just to check are we actually getting sort of emergent behavior of these mid-return prices that match our data, even though we don't train on this, right? So we're training on individual tokens of messages. There's no component in the loss that actually says you need to track the mid-price return. So this is emergent from this very low-level characteristic. And we see it works relatively well. Maybe the mid-prices are relatively easy, but also on the inter-arrival times that I've shown before, there are problems with these very nanosecond precision, high precision timestamps. You can see that these actually match the distribution relatively well. If you look at the histograms, so these are on the log scale. So it's not perfect, and you can see the QQ plots, but it definitely learns. It learns something that's relatively close to the data. Then we also looked at the sequence perplexity, which is a common score in language models, which basically it's just the gives you an idea of how surprised the model is by the actual data. So would it predict the actual data out of sample? And you can see, these distributions look relatively benign with relatively low sequence perplexity. And just as a benchmark, if you were to sample uniformly over the syntactically valid tokens for the next prediction, you'd get a perplexity of 418 or 419. Okay. So then the next question we asked ourselves is, well, what can we use this model for actually? Can we get something like a forecast, even though we didn't train on this model doing forecasts? If we look at mid-price returns, for instance. So what we plotted here is the correlation of the mid-price returns out of sample with the actual mid-price returns. And you can see we're not actually training on this, but it works relatively well of getting you significant, statistically significant positive correlation with future prices. So you can use this even as a prediction model for, in this case, Google and Intel, for Intel even longer into the future. This is already quite a surprising property of this. Okay. Then I'll mention some of the open issues and future work in this direction. So I mentioned the semantic errors sometimes still happen in the generation of the messages. So this is why we're now beefing up the model with more parameters. We're training on more data. So far, this was trained on a few weeks of data, maybe 2-3 months of limit order book data. So essentially, there's years of data that we haven't really used here. And we want to look into longer sequence generation. So far, we've done 100 messages into the future. But if you compare that with a CGAN approach or other models that might train on like entire days, you can generate much longer sequences. Another thing, we need to validate this compared to the CGANs and the other models and see how it actually compares model to model. So that's currently ongoing work on the generative front. And then, as I said, also on the reinforcement learning front, we're also employing our JAX-LOB models. Okay, some brief conclusions. So the custom data tokenization allows for analogous training to large language models. I think this is the first paper that tries to do it this way instead of using a conditional generative adversarial network. And our autoregressive paradigm generates very granular microstructure messages instead of aggregate returns or emergent features directly. So in principle, you could use this model for whatever task you're interested in related to limit order books. And this interestingly offers, new directions in research and high frequency reinforcement. Thank you.